In this video, we're going to take a look at how to calculate the lines and curves of best fit for different sets of data. And a line or a curve of best fit, sometimes called a trend line or a regression, is either a linear or curved function that we can use to best represent the main pattern or trend of data when it's displayed on a scatter plot. Again, this is also sometimes called a regression function, and sometimes this will pass through some of the points on the graph, none of the points, or all of the points. But as you can see in both of our examples here, the line and the curve both follow the general trend or pattern of the data. So this year in Algebra 1, we're going to be focusing on two different types of trend lines or regressions. That's going to be linear regression, when we have data that follows a pattern that looks mostly like a straight line, either increasing or decreasing, or quadratic data, where we see part or all of a parabolic curve. So first we're going to look at our line of best fit, and we have some data here showing the number of months used and the approximate distances that were driven in miles for different buses in Fairfax County. And the first thing that we want to do is we want to determine the equation of the line of best fit. So in order to do that, we're going to come into Desmos. I'm going to split my screen here so we can see both these things at once. And in Desmos, once we get in here, I'll have to split that over. There we go. I'm going to start by creating a table to enter my data. So I have two options to do that. I can either click the plus sign and click table, or if I type the word table, one will appear. In the X1 column, this is where we're going to enter our independent data, independent variable. And in the Y1 column, this is where we're going to put the dependent variable. So the distance driven depends on the number of months used. So months is going to go in the X column, and distances is going to go in the Y column. So my X column, I have 6, 10, 12, 15, 20, and 27. And then in the Y's, we're going to fill in that data, just pulling it directly from our table that we're given. And then before we do anything else, we always want to make sure that we've put this in accurately, because if we have any errors in our data here, it's going to mess up our equation. So everything there looks good. And now we are going to look at the scatter plot of that data and see what it looks like. So as you can see, I can't see any points on the graph right now, but that just means we're not looking in the right place. So I'm going to click this magnifying glass. It'll say zoom fit, and that will take me directly to where those points are on the graph. So we click that. We can see our data here, and Desmos is dynamic, so it'll switch the scale up as you change your window. You can zoom in or out if you need to. But if we look at this, this seems to be pretty linear, right? There's no real curve. It looks like this data is following a pretty straight linear pattern. So we're going to go ahead and use a linear model. And we're going to tell Desmos that we want to do that by typing in the model for our linear regression. So I'm going to type in Y1, and as soon as you type the 1, it'll bump it down into the subset. And it's important to use that subscript because we want to make sure we pull from this data in the table. Then we're going to type the tilde key. It's usually directly beneath the escape key in the top left corner of your keyboard. And then we're going to type A x1 plus B. So if we think about the slope-intercept form of a linear equation, this looks pretty similar to that y equals mx plus b. But the tilde tells Desmos that we're doing a regression, a best fit. The subscripts tell us that we're pulling data from this table here. So now, if I look at the information that I'm given, we're not going to do too much with the statistics or the residuals here. Instead, we're going to look at these parameters, right? So this gives us a value for A and a value for B. And if I substitute those into my equation up here, that would be the equation of the line of best fit. And if I look at the graph, I can see that this line matches that data pretty nicely. So I'm going to go ahead and jot that equation down so that we have it. So that would be y equals, and then A was 2,419, my pen got lost there. Y equals 2,419.72. Then we have X, and then B was negative 5,362.44. Usually we'll have directions for rounding. If we don't, nearest hundredth is a good bet to use. So once we have this trend line, we can use this to make predictions, right? So this equation relates the number of months that a bus was used and the distance that it's been driven in miles. So now, if I have the number of months that I'm thinking a bus will be used, I can use this equation to estimate how far that bus is going to drive. So now, we want to use our line of best fit and determine which of these values here would be the best prediction for a bus that's in use for 40 months. So all we're going to do is substitute that into our equation. So we know that y is the distance driven and x is going to be that 40 miles. So we're just going to substitute that in, and then we can calculate that value. And if we want to, we can just type that right in here to Desmos. So 2,419.72 times 40 minus 5,362.44, and actually I don't need that y equals there. And that will give me my estimate here of 91,426.36. So the best estimate there would be the 91,400 option. So that's if we want to use the line of best fit. We enter our data into the table. We use this equation here to set up the linear model, and it's very important that you type that in exactly as it is here, subscripts, tilde, A and B, all that, okay? That's going to be important. And then we can use that equation to make predictions. If we had been given a distance and we wanted to solve for the number of months, then we would just substitute in a value for y and solve for x. All right, so we can also use this when the data isn't quite linear and instead it's quadratic. So I've entered this data here into my table, and I want to determine the equation of the curve of best fit, because if we look at this, this isn't going to be matched just by one straight line. Instead, we can really see a nice parabolic curve here that we want to model. So again, we're going to start with y1 and the tilde. And then we're going to have a x1 and then squared this time, because we want to use that quadratic model. Get out of the exponent, we're going to have plus bx1 and then plus c. Okay, so this is pretty much our standard form of the quadratic equation, y equals ax squared plus bx plus c. One thing that I often forget to do is to include the second subscript here with the second x term, so just make sure you include that. But once we have that, again, it's the same thing to pull out that equation. So we have our values for a, b, and c, and if we check that, if we round it here, we have 1.1 about for a, so that would mean that we can knock out c and d here. We have a value of 4.2 for B, so that matches up with both of these choices. And then our C value is negative about 4.9 if we round it. So here we rounded that to the nearest tenth, so that equation would be B, right? This g of x is function notation. It's just the same thing as saying y equals. So when we're asked to use the equation of the curve to determine g of 9, this means that x equals 9, and we're looking for the value of y. So again, we're just going to substitute that in. We're going to say 1.1 times 9 squared plus 4.2 times 9 minus 4.9, and we can let Desmos do this for us. So if we just type in our equation, 1.1 times 9, make sure we square it, plus 4.2 times 9, and then minus 4.9, and that will give us 122. So y would be equal to 122. So you'll see this used a lot of times in science. If we have information about different things, we want to make predictions or model data, we'll use this. You can use it in engineering, in medicine, anywhere where you're collecting what we call bivariate data with x and y values, we can use these trend lines. And we don't only use them for linear functions, you'll also see them used for quadratic like we did here. You could use cubic, you could use exponential functions, you could use logarithmic functions, and you'll look at some of those later on down the line, but really we're going to look for what fits best for our data and go with the model that best matches that.